Hello, everybody. Thank you for attending my virtual Odyssey 2020 presentation. My name is Nikolaos Flemotomos, and I am going to present you our work at SAIL on a linguistically aided speaker diarization system that uses information from speaker roles. And first of all, let's see what our task is and what speaker diarization is. So in its most generic setting, speaker diarization wants to answer the question, who spoke when? So given as an input a raw speech signal, what we want to do is to partition this signal into same speaker groups without having any prior information about the speakers in the conversation we want to diarize. And conceptually and traditionally, this task involves two steps. First, we want to segment the signal into speaker homogeneous segment, and this can be done either in a uniform way or according to some speaker change detection algorithm. And then, having those speaker homogeneous segment, we want to cluster those into same speaker groups. But there are specific problems connected to this type of clustering. And in particular, if the speakers within the conversation reside very closely in the speaker space in terms of their acoustic characteristics, then there is the risk of merging the corresponding clusters together. Also, if there is too much noise or silence within the speech signal, which probably has not been captured by a voice activity detection algorithm, then we may construct a cluster which only captures those nuisances. And as a result, this would affect the performance of the system, even if we knew in advance the exact number of speakers in the conversation. In this work, we are focused on scenarios where the speakers play specific roles. So for example, we may think of a doctor-patient interaction. We may think of a lecture where we have the teacher versus students. We may think of an interview where we have the interviewer and the interviewee, and so on. And the interesting thing about those scenarios is that different roles are usually associated with distinguishable linguistic patterns. For example, in an interview, we expect that the interviewer will ask more questions and the interviewee will answer those questions. Or in a medical conversation, we expect that the patient will describe their symptoms and the doctor will give medical advice, for example. So the question now is, can we use language and can we use those linguistic patterns to assist diarization? So if we remember the problem of diarization and its traditional approach, what we would do is, given the audio signal, first segment, and this would be typically done with a uniform segmentation, and then cluster. Instead, here we propose to also process the textual information, which typically would be given from an ASR algorithm, and use some external knowledge about the roles within the conversation. And given this knowledge, to estimate the profiles, and by profiles here we mean the acoustic identities of the speakers in the conversation. And now, since we have those speaker profiles, we can convert the clustering problem into a classification one, and thus we can avoid the potential problems and risks which are connected to clustering, as we mentioned previously. And now in the next few slides, I'm going to go into detail on what its submodule here is and how we have implemented those. So notice here that in the first couple of steps of our system, we only process the textual information. So given the text, the first step is that we want to obtain speaker homogeneous text segments. So in each segment, after this segmentation step, we want every word to be uttered by a single speaker. So ideally, we want a system that knows and can learn when there is a new speaker change in the conversation. Instead, for this work, we assume that there is a single speaker per sentence. So we will segment at the sentence level. And in order to do so, we view this problem as a sequence labeling or sequence tagging problem. We construct this neural architecture shown here, where initially we construct a character level representation of each word through a CNN subnetwork. We concatenate this representation with the word embedding of the corresponding word. And now this sequence of words here is the input to a BiLSTM CRF network, which predicts a sequence of labels. And our labels here are two. B denotes that a word is at the beginning of the sentence, and M denotes that a word is at the middle of the sentence, which essentially means every word which is not the beginning. So our sentence here is one sentence, which is all the words from one label B until the next one. Now, having those segments, we want to assign a role to each one of those. So given the domain that we're working on, we assume that we know already the roles in this domain. So we build an role-specific language models for the n roles that we have, and also a background language model. And for this work, we will construct n-gram models. And after we interpolate the language models, and by this symbol here, we denote interpolation, and all the weights that appear on those equations are optimized on a development set. So after we interpolate the language models, we can just assign to each text segment the role that minimizes the corresponding perplexity. Now, notice that up to here, we have talked only about text. In the next step, in order to estimate the acoustic identities of the speakers or the roles that appear in the conversation, we also need, of course, the audio. So here, we need to align the text and the audio. And if the textual information comes from an ASR system, which typically would be in a real-world application, then this alignment information is already available from the decoding lattice. So having now those audio-aligned segments, we extract a speaker embedding, which for this work will be an X vector for each segment assigned to a specific role. And we can now define as the role profile, or as the role acoustic identity, as the average of all those speaker embeddings which correspond to that role. By doing so, however, we assume that all the segments are treated equally. However, we cannot be confident really about all the role assignments. And the reason is that since we have conversational interactions, after our segmentation step, we may have some very short segments, for example, like even one-word segments like yeah, which do not contain sufficient information for the task of role recognition. So what we're doing instead is that we assign a confidence metric to each one of those segments. And this confidence metric is the absolute difference between the best perplexity that we had and the second best perplexity. And now we can again define the role profile as an average, but now for this average, we only take into account the segments for which the confidence is above some threshold theta, and this theta is a tunable parameter of our system. So after we have now estimated our profiles, we are ready to do our speaker diarization, where instead of clustering, we can have a classification module, like shown here. And we're following a traditional approach for diarization, where first we segment uniformly the speech signal with a sliding window. We extract a speaker embedding for each resulting segment, and we calculate the PLDA similarity now of each segment with all the role profiles that we have just estimated. And the role that we are assigning to each segment is the one that is most similar to the segment, or in other words, that maximizes this similarity score. So this is the system that we are proposing, and we are going to use and evaluate the system on dyadic psychotherapy interactions, where we have two roles, namely the role of a therapist and the patient. And we are also going to use some external corpora in order to train our sequence stagger and our language models. And here in those tables, I'm giving the sizes of the corpora that we're using for this work. I'm not going to go into detail into the specific parameters that we have used for our system and the several subsystems. I will just mention that the F1 score of our sentence stagger was 0.8 after 14 epochs on the validation set, and that the order rate of the ASR system that we're using was about 40% for our dataset, which seems a lot, but actually is kind of common for spontaneous medical conversations. And as our baselines, we will use an audio-only and a language-only baseline. For the audio-only baseline, we have the system that we have already mentioned, the traditional system that we have mentioned, where we have a uniform segmentation and then a PLDA clustering. And for the language-only baseline, we essentially have the first steps of our text-based system here, where we take the text, we segment with our sentence stagger, and we assign each segment to a role. And the only thing that we need to do in order to evaluate the diarization is to align the audio and the text here. And as I have already mentioned, if the text comes from ASR, then the alignment information is already available. Here are our results on the psychotherapy data that we have tested. We have used either the reference transcript or the ASR transcript, using our sentence stagger or an oracle text segmentation. Here are our U9 model baselines, and here is the system that we have proposed. And by looking at the numbers, we can make some interesting observations and get some interesting conclusions. First of all, if we compare the two baselines that we have, we see that the results are better with the audio-only system, which means that the audio stream, as expected, contains more valuable information for the task of speaker diarization. And this is why we propose using the language information only as a supplementary cue. What is interesting here to notice is that in the language-only system, comparing the Oracle text segmentation and the Tiger segmentation, Tiger-based segmentation, there is a big performance gap. And the reason for that is that the Tiger oversegments, and as we mentioned, we may have lots of short segments which do not contain sufficient information for our recognition. However, in our system, we use this information only in an aggregate form in order to average all the segments or the role segments to get the acoustic identity of the particular role. So such inaccuracies kind of cancel out in our system after this aggregation. A similar pattern is observed here if we compare the results using the reference versus the ASR transcript. And because, as we mentioned, we have a pretty high word error rate, we have a severe degradation of the performance for the language-only system once we use the ASR results. However, when the transcripts are only used for the profile estimation, as we are doing in our proposed system, then the performance gap is substantially smaller. Finally, what we see here is that if we estimate the profiles using not all the available segments, but only the segments that we are most confident about, then we have further performance improvements. And instead of the parameter theta that we had introduced earlier, here we are using the 8% of the best segments per session. And by best segments, I mean the segments that we are most confident about. And A is a parameter optimized on the development set. A first observation that we can make from this diagram, where we have illustrated the diarization error rate as a function of the number of segments that we are taking into consideration for the profile estimation, is that unless we use a very small number of segments per session, most of the time the performance is better than the audio-only baseline, which is illustrated by this dashed line over here. Also, if we compare those blue and red lines, what we see is that even though when we are using the sentence tiger that we have built, which is this red line, even though when we are using this, we have a slightly worse performance than using the Oracle segmentation, we observe that if we are able to choose carefully the number of segments to use, then the Tiger performance approaches the Oracle segmentation performance. To sum up with my presentation today, we propose a system for speaker diarization in scenarios where the speakers play specific roles, and we use the lexical information associated with those roles in order to estimate the acoustic identities, which gave us the ability to follow a classification approach instead of a clustering approach, which is a common thing to do in diarization. We evaluated our system on dyadic psychotherapy interactions, and we demonstrated a relative improvement of about 30% compared to the audio-only baseline. So this was my presentation. Thank you very much for attending.